Hello and welcome to the third lecture of this part of Advanced Materials Chemistry course. Today we will learn about the photovoltaics. Quick recap what we learned in last lecture. In last lecture, we understood the difference between metals, semiconductors, and insulators. Then we saw direct and indirect semiconductors. The direct semiconductors are where the maximum of your valence band is at the same p position up to the minimum of the conduction band. In indirect semiconductor, they differ. And in indirect semiconductor, in order to have a transition, you need lattice contribution. Then we saw intrinsic and extrinsic semiconductor. Intrinsic semiconductor are pure semiconductor, where no impurity is added, and like pure silicon or pure germanium. And extrinsic semiconductors are where the properties of intrinsic material are changed by adding some impurities. So those are extrinsic semiconductor where this is not pure. Then we learn donors and acceptors. Donors are species which donates electron to the conduction band. Similarly, acceptors are those species which accept electrons from the valence band. Then we learn a little bit of non-degenerate and degenerate semiconductors. Then how carrier transport takes place. Then PN type of semiconductors we learn, and then we also saw how a p-n junction is formed and how it works. We will see today the use of that in photovoltaics. Then we learn how the charge carriers are generated, then recombination and lifetime of these carriers. Lifetime means how long they survive in the excited state. That is the lifetime. Then we saw metal semiconductor contacts mainly, and we learned that the metal, when it makes close contact with the semiconductor, because of the work function difference or work function and difference between electron affinity of the semiconductor, a barrier is created, and this barrier is responsible for flow of electrons from one side to another side, and it restricts or it opposes flow in the other direction. So this is a rectification behavior where current flows in one direction and doesn't flow in the other direction. So this is a Schottky kind of diode behavior. Then we learn a little bit of semiconductor device building blocks. There are 4 semiconductor devices building blocks, and all the devices are mainly having any of these building blocks. These are metal semiconductor junctions, then p-n junction, then heterojunction, and then fourth is the metal oxide and semiconductor junction. So if you see any electronic device or semiconducting device which is functioning, you can definitely see that any of these building blocks are used in those devices. Now let us see about the photovoltaic. So first we try to see what is the source of radiation, the light which we are receiving on the earth. So if we see sun, it is very hot, and the surface temperature, or you can say outer surface temperature of sun is 5800 Kelvin. So when there is any body which is at higher temperature, it always emits a radiation, that we know. So it emits radiation in all the directions. And what is the source of for this energy, which is there in the sun? These two reactions which are taking place inside the core of the sun. These are the fusion reaction where deuterium, two deuterium fuse together and they give this much amount of energy. Similarly, deuterium and tritium they fuse and they give this much amount of energy. So this energy is continuously released inside the sun, and the temperature of the outer you can say surface of the sun is nearly 5,800 Kelvin. So the sun will emit radiation, or you call it a black body radiation, at this temperature. And so it emits in all the directions, and very small fraction of the total energy emitted comes to the earth. So total energy emitted by sun is approximately 4 into 10 to the power 20 joule per second. And out of this, you can say it goes in all 4 pi directions. And if you see the solid angle or the angle of the earth, the sun will be very narrow. And still it receives about 1,73,000 terawatt of the sunlight every day. That is the total energy received on the earth from the sun. And it is this energy is more than 10,000 times the world's total energy required. Whatever energy is required by world, it is 10,000 times of that. So as we say, the sun is at 5,800 Kelvin, and from our basic physics, if we learn any body which is at such a hot temperature is going to emit the radiation, and that radiation we can find out by black body radiation formula. And if you plot the radiation, it will come like this. So this curve is the top curve is the black body radiation curve, emitted radiation curve at 5,800 Kelvin. Now, this is the theoretical. If you measure the just outside the atmosphere of the Earth, this is the spectrum, the yellow one. So it is matching almost same to this ideal black body radiation. So this yellow part is the spectrum of radiation received at the outer surface of the Earth. And then as soon as this radiation start entering in the atmosphere, the gas molecules has different vibrational levels, and when it matches with the energy, it absorbs, the gas molecule absorbs certain amount of energy. And so similarly water molecules also absorb. So some part of this spectrum, like these parts are absorbed by these gases. So then what we receive on the Earth is actually this red part. So this was the ideal spectrum, which should be when somebody is at 5,800 Kelvin, and this is the actual measured spectrum just when it enters the atmosphere of the Earth. And when it comes inside atmosphere and it travels up to the Earth surface, we see that there are few bands which are absorbed, and these are absorbed by the molecules which are there in the atmosphere. So these molecules are like water molecules, CO2, hydrogen, H2O, and then these are the corresponding H2O bonds. Then we have oxygen also, and then ozone also at the little outer surface. So this spectrum, when it is here, actually the intensity is at the outer surface is 1353 watt per meter square. So approximately 1.3 kilowatt, which is quite high. And then as soon as it comes down inside the earth, so this much amount of total intensity or the total energy is reaching, which is less than this, and it is approximately 1000 watt per meter square, and direct is about 800 watt per meter square. So there are few things which I have mentioned here. It is like here AM1, here AM0, and so AM1.5 also, which is standard used. So what are these? This signifies this AM is air mass. So it is how much, you can say air mass is defined like mass of air with respect to the vertical height of atmosphere that light has to transverse before reaching the ground. So it is you can say a ratio of two distances. One is, suppose sun is at somewhere here, suppose let us consider. So the radiation will come in this way. So it will travel this much distance in the atmosphere. So this distance divided by the distance which is the minimum when sun is at the zenith, the ratio is called as the air mass. So when sun is at zenith, suppose in June at 12 a.m., then it travels the exact x distance. So at that time, air mass will be x by x 1. So then it will be AM1. Similarly, when in the evening it moves from this to this side, like from east to west, it moves. So it travels more distance in atmosphere. And so this is, then you can calculate by simply dividing this distance by this distance. So standard is AM 1.5. So at AM0, AM0 is what? When zero distance is traveled in the atmosphere. So it is just outside the atmosphere. It is called as AM0. And this intensity should be equal to or very close to the ideal theoretical energy, which is emitted by black body radiation at 5800 Kelvin, and it reaches at this solid angle, the solid angle which is made by Earth to the Sun. So here we receive about 1350 kilowatt per meter square or 135 milliwatt per centimeter square energy. And what is AM1? AM1 is when sun is at the zenith and it travels the same distance. This I have already told. And AM1.5D is an standard, one kind of standard where it travels 1.5 times. So this is a standard which is used in most of the solar simulator. Solar simulator is a device, or you can say instrument, which simulate the radiation or you can say the light in place of sun in laboratory. So you cannot always use sun for your solar photovoltaic measurements because it depends on at what time you are using. So at different times you will get different readings. Therefore, you need a standard instrument or unit, measurement unit, which gives you an certain standard amount of radiation. So for that 1.5 AM 1.5 is considered as standard, and the solar simulators they can produce 1.5 also. You can generate any air mass standard there. So 1.5D is when this is travel 1.5 times this distance, and that time the intensity received on the earth is 88.8 milliwatt per centimeter square. This is actually direct, means only when you consider the light, which is direct light coming from this to this. However, at the same point, you will receive some other components also, like scattered light from other sources. So the total 1.5 will be 100 milliwatt per centimeter square. So the total, so when we call it AM 1.5G, that is standard for both direct and diffuse light incident on Earth is 100 milliwatt per centimeter square. So direct is this, then some scattered light, some diffuse light, and all the lights, other lights other than this direct light, when they are added together, they are approximately 12 milliwatt per centimeter square. So then total is 100 milliwatt per centimeter. So this is a standard. So what is standard? One sun, this we define as one sun also. So one sun intensity is, you can call 100 milliwatt per centimeter square, or the same is 1 kilowatt per meter square. So you see 1 kilowatt per meter square and 100 milliwatt per centimeter square, they are same. Now this was as far as the solar irradiation is concerned, that is coming on the earth. So then what to do with this radiation? So we have solar cells. What are solar cells? So solar cells are those devices that take light energy as input and convert it into electrical energy. So when the light falls on a solar cell, it converts it into electricity, electrical energy. So this we have already know that the intensity received on the earth is 1 kilowatt per meter square. That is 1.5 standard. So 1 kilowatt, if you can, what is it means? So in physical meaning, suppose you have a panel which is having 1 meter length and 1 meter width. So the total light falling on that panel will be 1 kilowatt. 1 kilowatt is a, you can say, very high power. So suppose nowadays we have one bulb which is approximately 20 kilowatt, 20 milliwatt bulb. So you can imagine this power is equivalent to blowing how many bulb? Nearly 50 bulbs. So imagine in 1 meter by 1 meter of the area, the sun is giving us that much amount of energy, and that is free of cost. So can we convert that entire energy or you can say entire incident radiation to the electrical energy? That we will see how it is converting. But important thing to learn is that the conversion efficiency is very important. If we convert 100% of that, that means our most of the energy problems will be solved, but 100% conversion is not possible. We will see how much. So even if we can convert 10% of that entire, that will also be quite a encouraging. So why solar cells are important? Number one, it is renewable energy. The energy source is there and is renewable. Then it is clean and non-polluting. then high power to weight ratio, then easy installation and minimum maintenance. Once a unit is installed, there is no need for it requires a minimum maintenance. Only cleaning those parts are required and regular checking of the contacts, nothing else. You don't have to add anything. Then there is no fuel costs involved or fuel supply problems. It have long operational lives. We'll see in few slides that we have solar cells which are working for more than 40 years and having the same efficiency. Then it does not produce noise, so noiseless and very useful in the remote locations in sea, in space where you can not lay the wire. Suppose you are traveling in space, suddenly you require for some unit or some device power, and you have run out of power. See, there is no electrical connection there. So you can, if you have a solar cell, you can just put that solar cell inside the sun and you can have the electrical power which can drive your device or instrument. Then there is no waste material. These are some of the, you can say, why solar cells are important. Then there are some issues also with the solar cells. What are those issues? Solar power cannot be obtained in the night time, obviously, because there is no sun. Then solar panels are relatively expensive. So initial cost is there, but once the advanced technologies and some organic devices will be commercialized, solar cells, then they will not be very expensive. Even the silicon panel nowadays is not very expensive. This is one can afford. However, still slightly initial cost is there. And the next thing is that energy is to be stored in the batteries, because if you see in our households, we require AC at 50 hertz. However, in the solar cell, the energy which is created is DC. So first that whatever energy is generated need to be stored in the batteries, and from the batteries using an inverter, you convert again into an AC and then supply to the grid or supply to the or use in your household domestic appliances. They need large area of land to produce more efficient power supply. So this is also an important point, because suppose you for like 1 kilowatt, 2 kilowatt, it is fine. You can put a small unit at the rooftop, and however, if you want to make a power plant, suppose you want to make a 1 megawatt power plant, in that case you require several square kilometers of space where only the solar cells will be stored. So large area is required. So that is also a problem. But there are spaces also like desert, like in high Himalayas, where nobody is there, one can install these things. Yeah. Then there is issue with the tilt and alignment of panels. So it is very important that the sun should be falling, the sunlight should be falling on the solar cells. Now, in the morning, sun is in the east. In the evening, sun is at the west. So even if you make any angle, you will not have your solar panel will not be facing all the time the sun. So you can have an arrangement that as the sun is moving, automatically the panel is also start moving, but that is also a very expensive arrangement and require a lot of maintenance. So that is not a practical solution. So but definitely there is issue with the tilt and alignment of the panel. So what angle you will fix which is the optimum one has to decide, and then all the your panels are fixed at that angle. Then there are cleaning issues, like main cleaning issue is that dust is accumulated on the solar panels, and when these are in the power plants, there are large area cleaning of all those solar panels is a problem. It is not so simple. So these were some of the advantages and limitations in the solar cells. Now let us see how this solar cell technology has evolved over the period of time. Initially, the solar cell were developed in 80s, and now we have now we are in 2024. So the solar cell, based on their technologies, are basically divided into three generations. These are the first generation, second solar cell, second generation solar cell, and third generation solar cell. In first generation solar cells, these were mostly wafer-based solar cells. The second generation solar cells are thin films based solar cells, and third generation, this is an emerging technology, mostly organic, hybrid, perovskite, DSSCs, this kind of or quantum dots, these kind of solar cells. So in first generation solar cell, there were two main, you can say, devices, kind of devices which were available. One was the monocrystalline silicon solar cell and gallium arsenide based solar cell. These are the single crystalline, both silicon single crystal and gallium arsenide single crystal. And then we had polycrystalline silicon, where in place of the single crystal wafer, wafers of polycrystalline silicon materials were used for fabricating the solar cell. Next comes the second generation solar cell, which is the thin film base. So here we had to use the wafers. Wafers are slightly thicker, maybe maximum is 1 mm, but still even 1 mm is quite thick. So a lot of material is required. So the second generation thin solar cells use very thin films, and these thin films are made of amorphous silicon. And then the type of solar cell which used amorphous silicon is called as amorphous or ASI silicon solar cell. Then we have cadmium telluride solar cell and CIGS solar cell. So these three are under this category. Then we have now third generation solar cells. Mostly these solar cells are not commercialized at the large scale. So a lot of research is going on at several places worldwide. So these are the different kind of solar cells under this generation. These are organic solar cells, dye sensitized solar cells, perovskite solar cells, and quantum dot solar cells. So one by one, we will see all these kind of solar cells. What are these solar cells, how they work, and how to produce these. So let us try to understand first, before we go into making and learning other things, that how a typical PN junction solar cell works. All of these use PN junctions for converting electrical energy into light energy. So this we learned yesterday. We have silicon, P-type silicon and N-type silicon. So this is our valence band. this is conduction band. And in N-type semiconductor, N-type silicon semiconductor, where is the Fermi level in N-type? It is close to the conduction band. In P-type, where is the Fermi level? It is close to the valence band. So it is Fermi level. Now you have the blocks of N-type and P-type. As far as they are you are separate, there is no problem. But if you fuse them together, we saw that yesterday also with the animation how the electrons and holes are moving from one to another, and there are two processes eventually which takes place is drift and diffusion. So first diffusion due to the concentration gradients, and then because of the diffusion and a potential is developed, and because of that it try to pull electrons or carriers or try to stop their movement, which is taking place due to the concentration gradient, and an equilibrium is established. So now you see when they are joined, the Fermi level are, there is an abrupt change at this point in the Fermi level, which is not allowed. So the first thing is that these have to come into equilibrium, and so that the Fermi level is aligned. And how it happens? It happens by both drift and diffusion. So when we join, p-n junction is formed and flow of electron and holes takes place, and the Fermi level they align. But when the Fermi level align, the situation is not exactly what we are seeing here, but it should be like this. So there is a gradient or a built-in potential is developed because of the flow of electrons from one, so you can say one type of material to the another type of material. So you have this VB generated, and then the Fermi level is at the constant. And why it happens? It happens because of the diffusion and drift processes of the carrier transport. Now you just add these 2 points with the external load. So now it has become our solar cell. Now can we add simply a metal wire with this semiconductor? Can anyone tell? Well, we learned yesterday, if we join a metal with a semiconductor, it makes a Schottky contact. So then here also you are joining a metal with the semiconductor. Here also you are joining a metal with the semiconductor. So now you will be having two back-to-back Schottky diodes, and therefore even if some current is generated, or even if you apply a battery in this circuit, it will not give any current. In most of the cases, the diodes will be back to back, but not always. It will depend on the barrier and this work function of this metal and electron affinity of this semiconductor, N-type semiconductor and P-type semiconductor. So what is the solution? Then in place of making a direct contact, people make the ohmic contact. Ohmic contact, there are, you can say, different processes for making ohmic contacts. These are also technologies how to make ohmic contacts, but in all the devices, in all the semiconductor devices, the ultimate contact is through metal only. And when there is a, you can say, when there is a point where this metal joins semiconductor at this place, there are always one has to make ohmic contact. So now what happens when a photon falls? If a photon falls, it will be absorbed and electron hole pair will be generated. And because there is a, you can say this VB, some potential is there, and this potential, because of this potential, electrons will be attracted towards this, and they will be pulled, and then they will flow in the external circuit. So you can just see this animation once more. Now, when this photon absorption, normally I have shown it in this side for just to explain. The process takes place during, you can say, this area. But it remains, it is actually same. There is one more difference. It is only for like understanding purpose. But when there is a illumination of light, in that case, Fermi level also doesn't remain straight. But only for one photon, if only one photon is incident, there is not much change. So we can assume this is the same. Now this is we have learned how solar cell is. What is solar cell? It is a typically we can consider it as an PN junction, and light falls on the junction, and electron hole pair is generated, and these electron hole pair are separated. Why they are separated? Because there is a built-in potential. If there is no built-in potential, they will stay there and recombine. When they will recombine? They will recombine after the, what we learned yesterday, there is something called as the lifetime. So up to their lifetime, they will remain in excited state, but ultimately they will recombine, and there are two kinds of recombination only. This also we learned yesterday. What are those two kinds? One is radiative recombination, or it is non-radiative recombination. If it falls from the, if it is absorbed this much energy and falls from this to this, and this energy falls under the visible range, the photon is emitted, and that is the radiative recombination. Or if it is like it doesn't directly come here but comes through different states and emitting small like energies, that energy falls under the it is not in the doesn't give photon. It actually goes in form of heat, and that is the non-radiative recombination. This was the solar cell. Now let us learn what are some important parameters for any typical solar cell. So let us see, this is our solar cell. We have a PN junction. There is a contact. We have made a contact here, and by making ohmic contact to the surface, then there is a top contact also. So, and then you have put a load here. That load can be any bulb also you can put small resistance, and then put, and you, in order to measure what you will put, you will need to put two devices, emitter and voltmeter, so that you can measure the voltage, you can measure the current, and this is the some load. You can have bulb or anything, whatever. So let us learn what are those different parameters. Whenever you see a solar cell, these parameters you should be knowing, or you should come across these you can say terms. You should be knowing what is the meaning of these terms. So first thing is the open circuit voltage. Open circuit voltage is, as it signifies by the name itself, open circuit means the circuit is open. So that means we just remove this resistance. There is nothing is connected. So this wire is also open, this wire is also open. So when there's nothing is connected, so actually there will not be any current, because there is no circuit to pass the current. So this voltage, when we measure without passing without passing any current, and that is the, you can say, maximum voltage possible, which is generated by the solar cell. That is called as the open circuit voltage. So open circuit voltage. Next is the short circuit current. What is short circuit current? Now in place of putting this load, just you short it by this wire, simple wire. So what will happen here? Now the voltage will be zero, because you have already shorted this terminal to this terminal, but the current will be maximum. So this is the maximum current which we can draw from a solar cell. But the situation is what? Now the voltage is zero, the current is maximum. In open circuit condition, what was there? The current is zero, but voltage is maximum. But are these, you can say, situation practical? Though we know this is the maximum voltage and this is the maximum current, but these are not, you can say, use of any practical purpose, because for any device you need both voltage and current, and the power is voltage multiplied by the current. So if I just, you just draw your attention to this curve, this curve. So here it is voltage, here it is current. So if I see at this point, when I have shorted, I am getting the maximum current, but the voltage is zero. On the other hand, for the open circuit voltage, now I am at this point where my current is absolutely zero. So if I try to calculate the power drawn from this solar cell, at this point is zero, and at this point also zero, which is not practical. So we have to draw the power. So as soon as we try to draw the power, the curve doesn't remain like straight or like this. It moves in this manner, this fashion. So this is the power. So at any point, let us consider 2 points at P1. So corresponding to this load, what is the power? It is at this voltage, this V multiplied by this current. This current. At this point, what is the power? This is this much and this much. So I can roughly say, or not roughly, it is exactly I can say that this area is the power which is drawn at this point from the solar cell. Similarly, at this point P1, I am drawing the power which comes under the area of this curve. So similarly, I keep on moving the point and try to calculate the power. What is the power being drawn across this load line? So I will find a point which gives that is we call P max point, which gives me the maximum area under this curve. So this is the power. So we want this. We want to draw. We want to always operate our. We wish to operate our solar cell on this point. So this point, the P max point, now is important in defining fill factor. What is fill factor? Fill factor is the fraction of maximum power that can be extracted from the solar cell, and it is defined as the fill factor. So as we saw, ideally what we want at VOC ISC current. We know our solar cell can give the current. It has a capacity to give current which is equal to short circuit current. We also know that it has a capacity to give the voltage which is having the value VOC. What we want at VOC voltage ISC amount of current. So that will be the maximum theoretical power possible. In ideal case, when I can draw somehow, which is not possible practically, at VOC I can draw ISC. So that will be the maximum, and how much it will be? It will be under this area. So it will be like ISC. So it will be this area. So the ratio of this area and this area is called the fill factor. So what is ideally maximum possible power that if I divide if you divide the maximum power with the maximum possible power, that is Im into Vm, that is called my fill factor. And now we know the most three important parameters, that is open circuit, short circuit current, open circuit voltage, and fill factor. We can define the efficiency also. What is efficiency? First thing is efficiency is how efficiently my solar cell is converting the light into electricity. So suppose I know very well that my input intensity is 1 kilowatt per meter square. So this is the standard 1.5 amps intensity. If I have a panel, if I am getting 1.5 kilowatt electricity out of that panel, in that case, I can call it as a 100% efficient solar cell. So efficiency is basically it is the output power or electric power generated by the solar cell and the input intensity on that solar cell. So how we will define this? This is the we can understand that it is first thing is how much maximum power we can generate divided by total radiated power. This is how much we can calculate by Vm into Im. It is P maximum Vm into Im and then divided by P rate. And this Vm into Im is by this formula. It is related to VOC and ISC. So VOC, ISC multiplied by fill factor and divided by the irradiated power. So because this point is dynamic and therefore we always measure for any solar cell, when you characterize, you measure open circuit voltage, you measure the short circuit current, then you measure an JV characteristic, or you can call IV characteristic. From that IV characteristic, it will be like this, we say this red line, and from this at each point you can calculate how much area, how much power it is giving, then find out the maximum power and divide that maximum power to the VOC into ISC, or you can VOC into ISC and divide it by that power, and then it will give you a fill factor. So it is not, it is actually a dynamic calculation. But once you find out a fill factor, the fill factor for that particular solar cell under that intensity, if you do not change the intensity, it will remain constant for that solar cell. So this is we learn what are, now we have learned what are solar cells. We have learned what are important parameters for the solar cell. Now we will learn what are the important processes in the solar cell which converts the light into the electricity. So the photovoltaic energy conversion involves 4 basic steps. What are those steps? First thing is the absorption. So it is very important that whatever radiation is coming or whatever light is coming, radiation I'm saying here, it is not like we generally consider radiation inside our center. Radiation means here I am talking about the visible UV visible or IR radiation which is coming from the sun. So just keep it in mind. Radiation doesn't mean alpha, beta, gamma rays or something like that here in this particular lecture. So first thing is that whatever light is coming, it has to be absorbed. Once it is absorbed, what it does, it excites the electrons from ground state to the excited state. So now electrons are excited to a higher level. It can be conduction band, it can be near to the conduction band. It can sometimes can be bound also, sometimes can be free also. Exciton also, exciton can be excited. So first, when light is absorbed, it is sure that electron will be excited from the ground state to the excited state. Now this energy, which is in the excited, when electron is having this excited energy, it uh, after that, in the second step, this is the electron and holes are converted into free positive and negative charge carriers, means holes and electrons. In the inorganic semiconductors. If we will come, when we will come to the organic semiconductor, we will see they're almost same but slightly different, where it is always exciton. Then there is a mechanism, there should be a mechanism to separate these positive and negative charge carriers. So first thing is that when light is absorbed, electron and hole pairs are generated. They are bound initially, so they has to be separated. So electron, let us consider electron and hole pair are now separated, but they will remain at the same place. So before, if you keep them after the lifetime of the carriers or carrier lifetime, they will recombine. So before they recombine, we have to separate them. So once you have actually separated, they cannot recombine. So you need a mechanism to separate positive and negative charge carriers. If we just recall the animation, what is this mechanism? This is in that particular solar cell was provided by the built-in potential. And then once you have separated and you have moved them to respective you can say ends, then these charge carriers need to be collected at on the electrodes, and then after that, after collection, it has to move through the load also. Load means the resistance or the appliance which are there. So these are the only 4 steps. So first step is absorption of light. We should absorb the maximum light. If we can absorb the full light, that is very good. Then conversion of this excited energy into free positive and negative charge carriers. So electron hole pairs are generated if we consider the silicon case, silicon solar cell case. Then these electron hole pairs are separated from one place to another you can say area, and then these carriers are collected on the electrodes, and then these are moved into the loads. So we have to you can say ideally we want all the processes ideal, means all our light should be absorbed, entire light should get converted into electron hole pair. All those electron and hole pairs are means sent to their respective electrodes without any recombination, and then afterwards all those electron and hole pair are you can say moving through the load. That is the ideal process. If everything is ideal, we will have 100% efficiency, but ideal things are not possible. Let us see what are the losses which are invariably going to happen. First thing is that when light falls on any surface, certain part of that is absorbed and certain part of that is transmitted. I will not say absorbed, I will say on any surface, if light falls, certain part is reflected and certain part is transmitted. So it is falling here, some part is reflected and some part is transmitted or entered through this surface, any surface. Even if you consider glass or any whatever surface you want to imagine, some part is always reflected, some part is transmitted. What defines how much part will be reflected, how much part will be transmitted is the refractive index. So if Ni is a refractive part index, the fraction of you can say part which will be reflected invariably, you do anything, is you can calculate by N1 minus N0, where N1 is the refractive index of the this device material, or where the light is entering, the refractive index of that medium, and N0 is 1 for air. So you have 1 air and 1. So this much amount of light is always going to be reflected. कितना भी आप कोशिश कर लेंगे, this much amount is always going to be reflected. So these optical losses are there. So first thing is that the light is falling on your solar cell, but first loss is it is some part is going to be reflected. If that part is going to, suppose 10% of your light is reflected, so now obviously your solar cell, the maximum capacity it can have or maximum efficiency it can have 100%, 90%, because 10% is already lost. So then one is reflection and another is, so there is one more thing. See this light, when suppose this is your device, this is your solar cell device. So when light actually falls under this and the surface is thin, or this surface, not surface, this you can say thickness of this device is small. In that case, what will happen? The light will, you can say, transmit without absorption. So it can come here and it can absorb, it can transmit. So that is unabsorbed light which is leaking out. So these two losses comes under the optical losses. So how we can minimize these losses is by providing anti-reflection coating. The anti-reflection coatings are special materials which are coated on a specific length over this surface, and what they do not allow, you can say, reflection, or they minimize this reflection part. So possible solutions are anti-reflection coating over the top surface, and then texturing the soft top surface. If you can, in place of this straight, if you can make a zigzag of the surface, what will happen? Will and this is also like solar cell only. So if light comes here, so what will happen? This light will, though it, even if though it is reflected, it will come at this point and again it will face the surface. So there is a same amount of, you can say, same fraction of probability, or you say same probability of light being, same fraction in place of probability, same fraction of light uh, which is here, which was absorbed, or you can say transmitted here, will again be transmitted here. So you are texturing this surface help increasing the area, and it is, we can say, inclined also, so that helps in more absorption of the light. Then another is concentration. What are the concentrators? Concentrators are devices where the, you can say, intensity is concentrated. If I will give you a, just to understand, I will give an example of like every one of us has done that experiment in our childhood. The convex lens, you have a convex lens, and we put towards sun, and then we see there is small, you can say, dot. So that entire, you can say, radiation of the sun, which was falling on that convex lens, we concentrate that into a very small area. So suppose I have a convex lens of 1 meter square. So how much intensity will be falling on that? 1 kilowatt. And if I can, you can say, focus that, or that spot, the bright spot, which we used to use for burning papers. If it is of 1 millimeter square, so we can see we have concentrated 1 kilowatt power into 1 milliwatt power. So if if the intensity is high using concentrator, we can reduce the optical losses. One is optical losses if light is reflected. Then next is absorption of light. As I touched upon in the previous slide also, see, when light is, though it is transmitted, it has not been reflected, but still there is a possibility that if your, you can say, thickness of the device is low, it is quite possible to, means it can also, can say, without being absorbed, it can go out of the device. One is the thickness. There is another important thing, that is the band gap of material. So if you have a material which is having this band gap, so any light which is having energy less than this energy, which is the band gap energy. See, if it is passing through this material, it will not, the electron which is actually at the top of this valence band, in order to absorb this energy, it does not have any energy levels during this forbidden gap. So it will not accept any amount of energy which is actually less than this energy. So if the radiation is having an energy which is less than this band gap, in that case, even if the thickness is very large, the electron is not going to accept that, and that radiation is going to be transmitted without being absorbed. So band gap plays a very important role in the absorption. Okay, one is band gap. So even band gap is, so suppose you have energy, suppose you have a material of very low band gap. In that case, majority of the light will be absorbed, but whether you will absorb all the light which is having more energy than this, that also is not possible. It depends on the thickness also. So there is one is band gap, another is the thickness of this material. If thickness, so intensity which is you can say coming out from this I is equal to, suppose we have an intensity I0 which is falling on this surface, so e raised to the power minus mu t, where mu is the linear absorption coefficient of the material. So thickness, so material should have if material is having high absorption coefficient, in that case it can be the radiation can be absorbed in low thickness also, but we should be aware that thickness of the material and absorption coefficient of that material are also two important parameters other than band gap of the material. Band gap of the material is of the paramount importance. If band gap is not matching with the radiation, it will not be absorbed. And then when it is falling in the absorption category, to be absorbed category, in that case also there is the thickness of the that material that matters. So we have learned two things. One is the transmission losses. Another is transmission losses means the reflection losses, the light is which is reflected, and another is the absorption. How the absorption can be also. So the band gap of different material, if we try to plot, are like this. So these are the band gap which is converted into wavelength. How do we convert that? You know the standard formula hc by lambda is equal to energy. So E is equal to hc by lambda. So it is hc by lambda. So then you have the corresponding you can say wavelength is shown here in the energy, and this E is the band gap energy. So if we will see gallium arsenide material which is having you can say energy corresponding to this. Similarly, silicon is having 1.12 eV, and the if you try to use this formula 1.12 is equal to hc by lambda, you will find that lambda, the value of lambda comes fall nearly 1100 or slightly less than 11, so 1100 nanometer. So now imagine you have a silicon and you are passing the entire you can say sunlight, you are allowing entire sunlight to fall over there. So, and the thickness is sufficient, so there is no question that it is thin, so it is very thick also. So all the wavelengths which are having you can say lower than 1100, or the energy will be higher than 1.12 electron volt, will be entirely absorbed. So this, suppose this is the solar spectrum, this blue is the solar spectrum. So this entire spectrum will be absorbed inside the solar cell, and this all you can say will be transmitted, will not be absorbed at all. So if you can try to imagine when this part has not been absorbed, so the corresponding energy has already transmitted out. So efficiency can be when it is being when the silicon solar cell is converting that electrical into electrical energy. This is the maximum which can it can convert if the efficiency is even the 100% for this one. So with this, if we will see just for practical understanding, that the light which we are receiving from the sun, approximately the intensity, if it is just imagine if it is 1000 watt per meter square, so 44% of this 1000 watt is falling under visible light, 37% is between 0.7 to approximately this level, and 7% of light in ultraviolet range, which is below 400 nanometer. So if my solar cell is absorbing anything above visible light, then or you can say it is not absorbing anything above visible light, then the maximum absorption possible on the solar cell is 44 plus 7, that is 51%. So the remaining 49% is leaking out. So this way the absorption imposes or you can say band gap, it imposes or it gives the maximum possible value for the efficiency for any particular material. So Shockley and Quasier, they did lot of studies on like many processes, and they come out with a very good paper that defines the Shockley Quasier limit for each you can say each of these material depending upon their wavelength. This we will see in the next slide. So if I summarize the loss mechanism, these are in the solar cells. So incident light, it can first is straight away if it reflected, then there is a loss. So then, but if light is coupled to the sun into solar cell, then also there is possibility that it is not absorbed by solar cell. That then there is a loss, possibility of loss. But if it is absorbed, then there is also possibility that free charge carriers are not generated. So that is also a loss if free charge carriers are not generated. But if charge carriers are generated, then these charge carrier can recombine or these can be separated. If they recombine, it's a loss. There is no point of like them being collected by the external electrodes and passing through the external circuit. So then if these charges are collected at the so there they can recombine at the electrodes also. So if they are not recombined but they reach at the electrodes, and then then only they can pass through the external load, and that is the you can say so you can see these 4 important losses which we just studied in last few slides. So when the charge is collected at the electrodes, this also we know contact materials are very important, and then we have to take care of the metal semiconductor contact that we learned yesterday, and today also we have touched upon. See, these things are very important. This concept you should always keep in the mind. Then there are these recombinations. There are this also we saw. There are trap assisted recombination, radiative recombination, surface recombination, OJ recombination, and if they are non-radiative recombinations, then they lead to the temperature. So these are some losses which takes place inside the solar cells. So all these loss mechanisms, we ideally want there should not be any loss, but that is not possible. So what we can do maximum is we can try to minimize these losses in order to have. So well, same thing. I will try to explain in a different way. So suppose so far we have learned when your electron was at the top of the valence band. See, first thing is suppose the spectrum is very large and your material is only one. Suppose I have used silicon solar cell. So my material is silicon N-type and P-type. So band gap is almost same 1.12. If you can little bit reduce because of this impurity level, consider 1.1. So my band gap is 1.1 only. And I have the entire spectrum of the sun, which I saw. Just recall the solar spectrum of the second slide. So that entire spectrum is coming. Now, this band gap, which was here 1.1 electron volt, it is corresponding to how much? Nearly 1100 nanometer, nanometer of the wavelength. So it means the 1100 nanometer wavelength is sufficient for raising this electron from top of this band to the bottom of this conduction band. So now what a light which is having, you can say, little more energy than this. So it will do what it will do. It will raise this electron from this point to this point, because this is also allowed. It is not like if you can recall the difference between atom and difference between the solid, then there is a band. So all these energy levels which are there inside this band are allowed energy. So electron can accept the energy which is which will take it to this from this. If it was only atom, then the energy was only you can say a sharp line. So in that case, it would not be allowed here. So this energy is like electron will accept this energy, which is more than like 1.1 electron volt. And what will do from 1.1 electron, it will reach here, and whatever extra energy is there, it will actually reach up to this point. So what it will do with this energy, this will they are in the conduction band, which what we learn that it's a continuous. So all energy levels are possible. So it may slowly, you can say, by accepting all the energies, it can fall to this point. So during this, like, it will lose all that energy. So what is this? Is very small amount of energy, and this will go into the heat. So ultimately, this electron which is here, it will come down to this level. Just this. So now, if the energy is more than Eg in that case, or the energy is more than band gap, then what will happen? This electron, which was here or even here, it will absorb the energy and it will reach at much higher position. However, if the energy is less, this also we have learned, we have emphasized on many times, that then it will not be absorbed, it will simply pass through. So only the spectrum which is having energy more than this energy will be absorbed. So all these, like, except in ideal case when it was 1.1 EV energy, photon is absorbed from this to this. This is the you can say the optimum value. This, if electron absorbs more energy and reach here, this loss, it lose the, you can say, extra energy in form of heat and comes back to this point before it is being you can say swept by the built-in potential. Or even if it is going moving under built-in potential, then also it would prefer to come at the bottom of the conduction band, because that is the minimum possible energy. Every you can say system want to achieve the maximum, you can say minimum possible energy. So if electron is here, this will try to reach at this point, and actually it will prefer to reach at this point only, but to transition from this point to this point requires certain, it need to follow certain rules. So because of those rules, immediately it doesn't come here. So this is this loss is called as the spectrum loss. What is spectrum loss in that case? So that energy which was actually equivalent to 1.1 electron volt is the optimum. Any energy of the photon. So one photon can excite only one electron here in this case. Now it is not like that. So if electron was having say 1.5 eV energy, so it will excite only one photon. So 1.1 eV will be like energy used for means energy used from reaching from this to this, and the remaining 0.4 eV it will have in the form of, it will be 0.4 eV above this level, and that will be actually it will not be converted because it's only one electron and photon, one electron and hole pair are generated here. So this will not contribute in the electrical energy through the external circuit, rather it will be wasted in form of heat. So that is also a loss. So this I explained, and then there is another loss which is actually impedance matching. This also we know from our basic electronics that if you have like connecting two circuits, in that case impedance matching is absolute necessary. Otherwise, the power will not be transferred from one you can say circuit to the another circuit. So when we are putting a load, the impedance matching is also important. So that loss are also there. Then there is the recombination loss. This I have already explained. And why recombination? As I said yesterday also, we saw there when they are the electrons are excited, they have a certain lifetime, and after that lifetime they will recombine back. So the rule is like the absorption is allowed, emission is also allowed. And then another is black body radiation, because the solar cells are at certain temperature, so they are emitting the radiation, black body radiation. So this also is approximately contribute nearly 7% of the losses. So if we you can say go through this, so only, so if the band gap, now we will just compare to the band gap. We want all the photons in the solar spectrum should be having for the silicon. If they are having 1.1 electron volt energy, that will be the ideal for me. All the photons slightly like 1.11 or something like that. So then all the photons will be absorbed and they will be like used for raising electron from absolute conduction band, valence band to the conduction band. So I want that much, but unfortunately it is not the case. My spectrum is having the entire you can say range. So this is, suppose I say the energy. So if my band gap is 1.1 electron volt, in that case I can have maximum this much usable energy. If it is 2, I can have maximum this much usable energy. And where these loss are, because the loss is actually this is 100%. So this 100%, if energy is less, if energy is less, then suppose 1 electron volt or energy is very less, in that case, mostly it is in the relaxation of band edges. And if it is like more than that, it is in the below band gap photons. So with calculating all these losses, the Shockley and Pessier, they came on a very famous paper, and they gave Shockley-Pessier limit for different materials. So for like gallium arsenide, if you consider all the losses, the maximum possible efficiency can be achieved is only this much. So you cannot have uh, efficiency for gallium arsenide solar cells, which is more than this efficiency. So this is the theoretically possible maximum efficiency for the gallium arsenide solar cell. So suppose you have a silicon solar cell. So what is the efficiency? It is nearly 33%. So with the silicon solar cell, if you made everything ideal, even then the silicon will remain silicon. It cannot, it will always, it will have a band gap of 1.1 electron volt, and it cannot, under that circumstance, it cannot, you can say, have an efficiency more than 33%. So ideally, theoretical maximum possible efficiency for silicon cell is 33. You cannot have more than. So for this purpose, they accounted all these losses which we just now discussed. They are spectrum losses, black body radiation, recombination possibility, impedance matching also. So now we have seen what are the different losses, what are all kind of conversion mechanism, how the light is being converted into electricity. So we understand that the material which we use should be having certain properties which will help us to make or to have good solar cells. So what are these? For appropriate semiconducting material selection, we should have optimum energy band gap matching with the solar energy. It should have high absorption coefficient for low thickness per cost. It should have good carrier mobility. Why it is necessary? If electron and holes are recombined, these carriers should move faster. So if they are not moving faster, the mobility is low, they can recombine. Then large carrier lifetime. Large carrier lifetime allow the carriers to stay in the higher, you can say, levels for a longer time. If the lifetime is low, in that case, what will happen? They will immediately recombine before being separated. Then large built-in field for effective charge separation. So if built-in field is large, in that case, the charge will be separated faster. Then large diffusion length. Diffusion length should be large. That is the length before. What is the large diffusion? That is the length before it is being absorbed. The radiation is being absorbed, and then small surface recombination. There should be less recombination on the surface. Then, in order to have minimize the reflection losses, you can have anti-reflection coating, texture surface, multi-layer coatings. This we also see. Then for reduce the series resistance. The series resistance is the resistance, or you can call it the contact resistance also. So you require better metallic grid design and high conductivity contacts. In addition to after making the ohmic contacts, and then improve transparent conducting coatings. So this they are like certain materials which are conducting and which are transparent also. So N-type or ITO tin oxide, that is indium doped tin oxide, it's pure tin oxide. Zinc oxide also, then dip zone zinc oxide also, that is N-type TCOs. And PTA TCOs are actually not very well developed, and they are not commercially used. They are only used in like laboratory scale when we are doing experiment, trying to understand how they work. So based on the types of crystal used, silicon solar cells can be classified in 3 categories. Number 1 is silicon crystalline silicon solar cell, polycrystalline silicon solar cell, and amorphous silicon solar cell. So single crystalline solar cells are the single crystalline or monocrystalline silicon cells are produced from the pure silicon single crystals. So you have a single crystal, pure single crystal, large single crystal, make wafers from that, and the wafers, the thickness of wafers can be they are usually less than 1 millimeter, and then it's a single crystal, and that is used for the making solar cells. So efficiency of these solar cells are higher, and let us see, try to understand the how the solar cell is fabricated. It will, I think, sometime. Okay. So let us see how we fabricate the silicon solar cell. So let's say pure starting material is a P-type silicon. Consider wafer. So wafer is always having you can say two surfaces which are you can say damaged because it has just cut. So then you can saw those damages and then etch. And so then texture it can be chemical etching also, it can be sand blasting also, so you increase the area. Then so it was P type of you can say material. So on that material you dope phosphorus. Why there are different methods of doping phosphorus. So we will not go into detail of those methods, but consider that we are doping phosphorus. So this wafer is kept in an atmosphere where it is phosphorus rich. Let us imagine in this way, and then that is phosphorus is being absorbed on entire this surface. So now you have a wafer which is placed there. So phosphorus will be absorbed from the all side, and suppose this red area, it will become the now phosphorus doped silicon, which was initially P type. So now this will become N. So it is P, now it has become N. So now you see it is P and it is band. So we have already made now PN junction. Now what we should do, see this entire thing is actually connected. So this connection has to be removed first. So first we cut this part. So we have cut now this diffuse part. So we remove that. Then the anti-reflection coating is deposited over that. And then afterwards the conducting piece, you can say conductive connections are made. Before that you make you do certain other coatings also, like titanium etc., for making a ohmic contact, and then afterwards the back contact are printed here, and then there is a firing. By that you can remove that part, and so with co-firing you get this kind of thing. So this is the typical if you magnify the solar cell which are like available, then you will have a like this kind of structure. And this is a typical IV characteristic view, the voltage and current characteristic of this solar cell. So we at like BARC also had taken up this technology for development of solar cells for specific space applications. These solar cells were not available in India in like 60s. So BARC has taken up to develop these solar cells for our space applications. There it was required, and the solar cells were not given to us. So this I'm telling the standard publication steps taken from the document available. So phosphorus was diffused to make 0.3 micron thick and type layer on the top surface of a P type of the silicon. and the size was approximately 20 millimeter by 20 millimeter square or 10 by 20 millimeter square. Then the front contacts, as I told in the earlier slide, were developed by first depositing titanium, then palladium, then silver, three layers of that, and the thickness was approximately 50 to 100 micron. Then anti-reflection coating, the material was used tantalum oxide, and it was done by thermal evaporation. Then these cells were cut into the rectangular square size, and the efficiency of these solar cell was 14.5%. This is the same thing like which I explained, but in a slightly detailed way, with more details like fine details, like you have P-type substrate which was taken. First it is cleaned, then it was heat to 850 degrees centigrade, then nitrogen were flown, and then the doping of phosphorus was done by this process, where it was actually POCl3. It was placed in the where POCl3 containing nitrogen was passing through it, and then pure nitrogen and oxygen ambient was there, and therefore now you had P, and over that, like in earlier slide, as I said, this was P, then and all four side of all four all side of that a PN junction is formed. Then cutting the sideways, and then back side contacts as deposit titanium, palladium, and silver, and then top side contacts was made by depositing paper deposition titanium, palladium, silver, and then on the top side anti-reflection coating was done using tantalum oxide, and then this packaging and module testing. So this is just a block diagram. These are the same solar cells. The photographs were taken 4 years ago. The solar cells which were developed in 1970 at BARC. And these solar cells were actually used in many of the satellites, some of the many of the experimental things, and some of the onboard satellites. Like Bhaskar 1 and Rohini, the solar cells were used. And then after maturing everything, the entire process, developing everything, the entire technology was transferred to BHEL Bangalore in 1984. And these solar cells, like after, if you can say, nearly 40 years, still these solar cells are working. So I will just show you the IV curve of these solar cells after, just to compare, and it will give you an idea how stable these silicon solar cells are. So these values of some of these solar cells are VOC was 0.6 volt, and the short circuit current was 38 milliampere per centimeter square, and field factor was 60%, and efficiency was 13.7%. These are the values which I have taken from the standard technology transfer document available at our center. So this is all the solar cells which were actually developed. It is not like that it is always 0.06 for all. It may be 0.59, but the variation was very little. So I have taken the standard one or average one. And then now if I measure some 810 solar cells, what I found, the average value of open circuit voltage now after so many years, it is 0.57 volt. JSC is this much, and so if you see, there is not much change. So if efficiency over 40 years have changed from 13.7 to 12.1, that means still these solar cells are working. We did some more experiments, like we changed, you can say subjected the solar cells under radiation. Now I'm talking about the gamma radiation, and there was no change in the parameters even up to 100 kilogray of the irradiation. That means these are very radiation hard solar cells, and the intensity was also varied from 5 milliwatt to 100 milliwatt. So, and temperature also varied from like up to 70 degrees centigrade. And so we conclude now that these devices, which were developed approximately 40 years ago, they are very stable, and we use these solar cells as a standard calibration in our lab after so many years, and they are very stable. So this gives you an idea that these solar cells which we develop have a very long time, a very long life. So only losses which are some context losses are there that can be repaired. You can make more better context. So if you develop a solar cell, the life is there is no problem that it will have a after 2 years or 3 years, it will go bad. It is not like that. So that was as far as the single crystalline solar cell is concerned. Now let us see some polycrystalline silicon solar cells. What is polycrystalline silicon cell? Where the single crystal is not used, rather than polycrystalline mass is used for the making solar cell. So what is the difference between polycrystalline and single crystal or monocrystalline? So in monocrystalline, entire mass or entire wafer is a single crystal. However, in case of polycrystalline, you have several small crystallites which are separated by grain boundaries. So these are cheap. Making a single crystal is little expensive. You need a lot of expensive, you can say, crystal growth systems to make single crystals, and wafers are very expensive. So why you need polycrystalline? Compositional control is less stringent, less energy intensive process. You don't need that big systems, and it is very economical. So in polycrystalline solar cells, liquid silicon is used as a raw material, and polycrystalline silicon was obtained followed by solidification process. So very, you can say, making a polycrystalline mass is very easy as compared to making a single crystal. Single crystal making is very, you can say, difficult and tedious process. We will see in, I think, fifth or sixth lecture, where I will tell how the crystals are grown for like silicon, gallium arsenide, and other material. And compared to those crystal growth things, the making a polycrystalline mass is very easy. Just melt it and solidify it. That's all. Nothing more. So melting is not a problem. You heat silicon, it will anyway at one temperature it will melt, and then after that you cool it. So you will have a mass which will be actually a solid polycrystalline mass. So the polycrystalline solid liquid silicon is used as a raw material, and polycrystalline silicon was obtained following the solidification process. As I said, the material contains various crystalline size, hence the efficiency of this type of cells is less than monocrystalline solar cell. And issues are like polycrystalline material quality is poorer because of the crystalline defects and metallic impurities. And diffusion lengths are lower as compared to crystalline silicon. Texturing is more difficult because of the different exposed crystallographic planes. As I said, the process is very simple. What is the process? You melt. First thing is that you take the silicon that much in a big like bucket, and then you melt it with raising the temperature, putting inside a furnace, or whatever way you want to raise. You can couple directly with the induction heating, and then once it is molten, then you fill in some you can say container and pour it inside this container. What will happen after some time? The you can say the heat will be you can say lost from all these surfaces, and this will start solidifying. And you see this entire chunk you are putting you are pouring liquid, but the things are getting solidified. So this will be this, but this will not be a single crystal. It will be a polycrystalline. So if you see, this is a single crystalline solar cell, and this is a polycrystalline solar cell. You can, by looking at the solar cell, you can make out which is the solar cell made from the single crystal or solar cell made from the polycrystalline mass. So for polycrystalline solar cells, solar grade material is used. Material is cast into rectangular blocks, as I just now explained, and the efficiency is lower. It is typically 13 to 15%. The best efficiency is 18%, ideal cases. So if I compare, if I make a performance comparison for like monocrystalline silicon, we have nearly 25 to 26% efficiency. These are also in the laboratory solar cells, not in the commercial. The commercial solar cells are having efficiency of nearly 18 to 20% for monocrystalline, and for polycrystalline, it is typically 14% for commercial. However, in the laboratory, for the you can get up to 22 to 23%. Then uh, this this was as far as the first generation of solar cell comes. Now comes to second generation, which is thin film based solar cells. Now, why we require thin film? Because one is in the wafer you need lot of material. So if you can make a very thin film compared to the wafer, you can reduce the material requirement, and accordingly you can reduce the fabrication cost, and then you have tunable material property, because it's a normally when you have a very thin film, there are many 2D rules applied on that as compared to long range 3D order, because in that the you can say in that particular direction the long range 3D is not that prominent. 3D means three dimensional. So important thin film solar cells in this category, thin film category, are amorphous silicon solar cells. So far we had studied crystalline solar cells. Then you can say polycrystalline solar cells. Now we have learned third silicon, that is the amorphous solar silicon. The amorphous silicon solar cell. We have cadmium telluride solar cell and copper, indium, gallium diselenide solar cell. So all solar cells in we will go quickly, because the things are same. You will have one P type of you can say layer, one N type of layer, and you have one intrinsic layer, and then radiation will fall and it will be absorbed. Electron hole pair will be generated, and they will be separated because of the building potential, and they will be collected to the outer. So technically, all these solar cells are almost similar. So that's why I will have an opportunity to move very quickly, and you will be able to understand. First, just before going to there, I will just try to explain what is the difference between monocrystalline. Though by the time you already know. So monocrystalline, it's actually like this. In all three dimensions, all atoms are at fixed distances. It is predictable once you are here that the next atom, where you will find the next atom. However, in case of amorphous, there is no order, absolutely zero order. So you are not very sure that in which direction you will get another atom at what distance. And there is another thing is that some bonds which are actually unsaturated remains unsaturated there. They are called dangling bond. They also create additional you can say energy levels. So if you see absorption coefficient, as I said in the slide where I was explaining the absorption part. So there were two things. One was the band gap, another was the absorption coefficient. So for like different materials, if I try to draw at different photon energy, the absorption coefficient, this is you can say different experimental curve. For like crystalline solar cell, if you increase the absorption coefficient increases in this way. So for like this, I want to emphasize here for the importance of amorphous silicon. So the absorption coefficient for amorphous silicon from starting from 1.4 EV, it is very high. So that will allow actually a little thickness of the amorphous silicon to absorb more radiation. So now how actually it is made. So amorphous silicon is obtained by depositing silicon film on a substrate like glass plate. And because we are not making a single crystal, so deposition process can be any like sputtering process, glow discharge, or vacuum deposition. because you are not controlling the you can say, or you are not placing the atoms, or you are not providing time them to you can say put sit on a particular lattice point, so you can deposit by any of these processes. The optical gap is high here, and it is having a very high absorption coefficient of nearly 100 times than crystalline silicon. This we saw in the last slide on that curve. So approximately 1 micron thickness is sufficient. Now, how much is 1 micron? If you this is just I written, or like if you take your one hair, the thickness of one hair is approximately 75 micron. So it is. So imagine how low means the thickness will be. So dangling bond can be reduced by, now there was one problem as of the dangling bonds, because there are many bonds which are unsaturated. So how in like fabrication commercial units, what is done? These dangling bonds are saturated by you can say reacting by or you can say hydrogenation. So then in that case, this amorphous silicon is called as hydrogenated amorphous silicon, or ASIH, where all the not all but majority of the dangling bonds are saturated by the hydrogen. So lower carrier lifetime and mobility in compared to crystalline silicon. This is the we can say this disadvantage that carrier. No, sorry, this is still advantage. Carrier lifetime and mobility. Low mobility is a disadvantage, but lower carrier lifetime is also a disadvantage, because in short period of time they will recombine. So both carrier lifetime, if it is less, that is a disadvantage, and if mobility is less, that is also a disadvantage. As a result, the efficiency of amorphous solar cell is much lower than that of the other two types of solar cell, but the price is very less. These are used mainly in low power equipment such as watches and pocket calculators, etc. You must have seen the calculators where no battery is required. There is actually a black strip just above that, and that is actually a solar cell, and this is an amorphous silicon solar cell standard. So this is same thing, like this is amorphous silicon. It was a dangling bond which was saturated. This is the typical layered structure. You have a glass, then transparent conducting oxide, then P layer, then I layer, and then N layer, and then metal contacts deposited. If we see the working, just you have a P type here. The energy levels, n-type energy levels, and the photon is absorbed here. Electron and hole pairs are separated. Then they are actually, you can say, moved or moved. These electron hole pair moves under this built-in potential, which is like this much difference, and then they reach at the electrode and collect it. So these are efficiency comparison, as we already compared between monocrystalline and polycrystalline. So if you compare with the amorphous, the efficiency of amorphous is very low. But if you can see that you are compensating in the thickness, the thickness is of this solar cell is very small, and so it is very cheap. You are using very less material. Thickness is because thickness is very low. So that is fine, and if you have some very low power devices where you can use these solar cells. Now let us say a similar second type of the solar cell is CIGS, that is copper indium gallium diselenide solar cell. So in this you have one is like there you had silicon. solar cells you require P-type and N-type material. So there in that silicon standard so far we have been seeing it's a silicon N-type silicon or silicon P-type silicon. So now here you are having one cadmium sulfide, and with these two you are making a PN junction. So what is N-type here? What is P-type here? So this is N-type material, CDS, and CIGS is P-type material. So now you have a PN junction. What is advantage? The band gap tunability by varium in this. If you see on the first day itself, we saw that compound semiconductors and ternary semiconductors, where the ratio, changing the ratio, we just explained there. So this is so by changing this ratio of gallium and indium, you can vary the band gap. So however, there is one little tricky issue is there. The composition control is required due to the complex. The phase diagram of this is slightly complex, and therefore making is actually not so straightforward. So then you have a heterojunctions between PCDS and copper indium gallium selenide CIGS and NCDS prepared by co-evaporation process. So now you have a heterostructure. Efficiency of these solar cell are typically 20%. And band gap of CIGS is graded by suitable composition profile of indium and gallium, as I explained here. So by changing, you can tune. So you can vary the band gap, and if you vary the band gap, you can change the what changes with the band gap. Can anybody tell? The band gap is actually absorption. So ITO and ZNO are used as a conducting and transparent conducting films. Now there is another type of solar cell which is based on cadmium sulfide and cadmium telluride. It is CDS, CDTE, or simple CDTE solar cell. So it has high optical absorption because the band gap is in the range of 1.45 to 1.5 eV, and cadmium chloride treatment is required to avoid interdiffusion between CDS and CDT layer. So you have two layers. There is a problem of diffusion in this those two layers. So this is the treatment is done, and the efficiency of these solar cells is typically 21%. That is also in laboratory only, and because cadmium is very toxic, and therefore that is the disadvantage to these solar cells. Now we see in a similar way 3-5 semiconductor solar cells. So band gap of gallium arsenide, C5, gallium aluminum arsenide, and gallium indium arsenic phosphide materials can be easily varied by composition. As I if you vary the composition of these elements, you can have varying band gaps. So that is the advantage with these solar cells. And best solar cells prepared by metal organic, CVD, or MB. So this 3-5 solar cells. The multiple junctions to achieve high efficiency. What are multiple junctions? So you have actually one layer. You have a one independent solar cell, and you have another independent solar cell above that. And then you have a similar way. You can have many solar cells. So you are putting one solar cell, then another solar cells, and then another solar cell, and joining the electrical output of all these solar cells in series. And so you can enhance. So what is the advantage? Advantage is that suppose you have a high band gap material at the top. In that case, what will happen? It will absorb all the energy, but up to that band gap and pass the remaining one. So now it goes in place of like it is going waste. There is another material which is below that, which is having lower band gap compared to that, and then it will absorb the remaining. So that way you can use it by using multiple junctions. You can achieve higher efficiency. So more than 40% of efficiencies can be are achieved. है ना? So in single junction, as we saw, the theoretical limit itself is around 33%. But in laboratory, people have achieved up to 27%. That is the maximum one has achieved. So in like multiple junction, you can have about 40% efficiency. So these cells are highly reliable and radiation resistant due to high material and fabrication cost. But though these are highly reliable, but they are very expensive also. Just keep this in mind. So due to high material and fabrication cost, these cells are mainly used for space or concentrator applications. So now we just see a typical multi-junction solar cell, which is made like this. So you have a bottom cell here. There's a bottom cell, then there's a middle, so you can say cell, and then there's a top unit. So now at the top unit, you have the highest band gap like material. So it is 1.86. So corresponding to 1.86, suppose this when light falls from the top, and this is the entire spectrum which is falling, this is the entire spectrum which is falling on this point. So what will happen if this is the like 1.86 ev, so 1.86 ev is corresponding to somewhere here. So this entire you can say this entire part, this will be actually absorbed in this solar cell, and this will absorb, and accordingly it will give some certain you can say electrical output. Now this part, which is the leftover part, this entire part, this part will actually move, and it will come from this side to this side. Now you have another solar cell where the efficiency, why it will not pass, can someone tell? I have already explained multiple times. We should be able to tell now. Because of the band gap. Okay. So now this much will be, this entire spectrum will be passed from this solar cell. It will come to this, the middle one. So middle one is having you can say band gap of 1.4 ev, and which is having the energy corresponding to this point. So entire, you can say this area will be absorbed by the middle one. However, any radiation which is having energy less than 1.4 ev will not be absorbed up to this level. It will still pass. Now you have the lowest band gap germanium solar cell, which is having 0.65 ev, and up to 0.65 if you calculate using that HCY lambda, up to what wavelength this 0.65 electron volt will give, you will be able to find yourself that it will be somewhere here. So the single cell, solar cell or single junction solar cell, which was absorbing only this part, has now actually is now able to absorb the entire spectrum, this entire spectrum. Okay. Okay, so that way, so you have that way the multiple solar junction is yours. So now can someone answer me a question? If I will actually use only germanium silicon, only germanium solar cell and pass this entire spectrum, will it not absorb this entire spectrum? So if it will absorb this entire spectrum, so my absorption problem is solved. Then why do I need three different layers? My problem was that the first was not able to absorb any spectrum above this range. So that was my problem. That's why I used another one, which was now I have a solar cell, which is actually I have placed at the bottom. If I entire solar spectrum I allow to fall on this solar cell only, it will absorb entire spectrum. What is the problem? Band gap is 0.65 electron volt. So why I am doing this, making three different solar cells with different three junctions and using very expensive like procedures, gallium arsenide, gallium, indium gallium phosphide, and the complex procedure of joining them together. Why it all is required? If absorption, I can give you a hint, you have to think the answer. I may ask that in the exam also, I may ask in the assignment also. I can give you a hint. The absorption itself is not sufficient. It will absorb 100%. That is true. It will absorb this entire spectrum. But whether it will be sufficient to make or you can say to give necessary efficiency, think about that and answer yourself. You will get. I am very sure that you will get the answer. So this type of best solar cell has given efficiency of multiple junction efficiency of nearly 43% at 400 sun. 400 sun means you can say the concentrators can be as I gave an example of simple convex lens, can be convex lens, but normally these are not convex lens, these are reflectors. So you have mirrors, big mirrors. So where the solar you can say radiation is concentrated in 400 times less area. And at 400 sun means if you are using with the concentrator, and intensity 400 sun will one sun is how much? I have already told you, 1 kilowatt per meter square. So how much light or you are actually providing at that point? It is 400 kilowatt per meter square. So this is the typical just a like same solar. See this in 3D. So with this, I come to end of this lecture. If you have any question, I'm ready to answer. Well, if there is no question, then let us close today. Thank you so much. See you in the next lecture, where we will see organic solar cells and thermoelectric. Thank you and bye.